Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking IBM Watson for sponsoring today's event. IBM Watson is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had an opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled Deep Learning from Basic Principles Through Training Models, and that's going to be presented by IBM Watson. But before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We have one presenter who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation. And now we'll be reviewing and presenting them on your behalf during the Q&A portion of today's presentation. Well, I'm very pleased to introduce today's speaker, Anthony Stevens with IBM Watson. Anthony is Offering Manager for Watson Deep Learning, where he collaborates with IBM Watson Research to translate theory into practice. Previously, he was Senior Watson Architect working with over 40 customers to include partners, engineering, and research teams to architect cognitive solutions using Watson technologies. Now, Anthony is an expert in transforming complex problems and data sets into elegant mobile, web, and cloud solutions. He's done this for life science, health, consumer, and multimedia companies by bringing deep expertise in both software development and product management. He's led the process to design, architect, build, and launch products for startups and Fortune 500 corporations. So, Anthony, thanks for being with us today. We're looking forward to your presentation. Now, what are neural networks, but more important, how are they trained in practice? How can data scientists design an optimal neural network with a single training run that can take 2 weeks? Now, in today's Data Science Central webinar, we'll start from the foundation of what deep learning is, then fast forward through what it takes to train a production quality neural network. You won't be able to train a network when this talk is over, but you'll understand enough basics to start a smart conversation about your customers' or company's practices of deep learning. So, Anthony, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Okay, well, thank you, Bill. Thank you, everybody, for attending this webinar. As Bill said, we're going to start with the basic principles and walk through how deep learning models are trained in practice. But before we start that, I wanted to do a quick poll of the audience and learn a little bit about who is on the call so I can tailor this presentation to the people that are attending. So the way we're going to work this call, this webinar, is to assume that in the beginning that you don't know anything about deep learning. But when we're done with the call, I hope you have a good understanding of how deep learning is practiced, what deep learning means, how neural networks are trained, and how they capture information in practice. And in the end, we'll walk through how deep learning models are trained by data science teams. So by the end of this call, you should be able to have an intelligent conversation with either your peers or your customers, and to understand that deep learning isn't just a fad, but that it's a wave of the future that we all need to pay attention to. So it's great to see that we have a nice blend of individuals on the call, a large number of people from research, so people that most likely have experience in building deep learning or machine learning models. Maybe even some business analysts would fall under the research side. Offering development, good to see that we have people that are building solutions. A few people like myself on the offering management side, as well as sales and marketing. I'll have to figure out who those others are sometime in the near future. So let's start out with what is deep learning. So an area that people get confused about is that we hear about terms like deep learning, machine learning, artificial intelligence, data science, and it's important to understand how deep learning fits into each of these areas of practice. So deep learning is obviously a subset of artificial intelligence, but it's also a subset of data science. So you can do data science without necessarily using deep and machine learning, but deep learning is a growing field of machine learning, which is an area of deep interest because it allows computers to learn patterns in data without us explicitly having to program those systems to understand and identify the patterns in data. We'll talk a little bit about why this is important, partially because programming systems to identify patterns in data is incredibly complicated, especially when we as humans have a difficult time identifying those patterns, or at least explaining how we identify those patterns. We'll also maybe touch a little bit on how patterns are recognized without explicit programming, because this is a problem where we're very used to our systems knowing understanding how our systems work. And now with the current state of deep learning, the systems are, for lack of a better word, black boxes. We don't exactly know what's going on, but an emerging and very vibrant field of research is to understand how deep learning and even machine learning networks are making the decisions that they are. And part of that is understanding this internal representation that the deep learning and machine learning algorithms make about the data that we expose them to. Now, first off, when we talk about deep learning is synonymous with neural networks. So synonymous with the idea of training artificial neural networks. And we'll see in a minute that while we talk about artificial neural networks, and they do mirror in some ways real biological networks, they're a grossly, immensely simplified version of a biological network. But we do have this similar concept, if you're familiar with biological neurons, of having data coming in to a dendrite, coming into the body of the neuron, multiple inputs coming in, and then a single output coming out of the neuron through the axon, and then that signal subsequently going into other neurons. And we'll describe this a little more. But if you think about why deep learning is important, it's permeating every part of our society. And this is just a small snapshot of the areas through which we see deep learning taking hold, from autonomous machine, security and defense. We hear about it in medicine, biology, and of course the internet. But I would expect and hope to see and learn many of the people on this call starting to apply deep learning in areas that are relatively untouched by the field right now. So there are a couple of reasons why deep learning has taken off so dramatically over the past few years. And it's really only in the past few years for really two reasons. If you think about deep learning, and even in what we've seen with machine learning, deep learning is seeing a rapid increase in adoption, partially because of improvements in the underlying mathematics, the ability to do what's called backpropagation, which is how these artificial neural networks are able to learn from data, but also due to the increased graphical processing capabilities coming from GPUs. So whenever you hear about deep learning, you'll want to think deep learning equals neural networks equals GPUs. Not that neural networks are GPUs, but that you cannot train today's deep learning networks without a GPU. Or, Google uses TPUs, but the underlying principle is the same. You're doing a large number of matrix manipulations, and that's why GPUs are so important, because GPUs, graphic processing units, were built to do very fast matrix manipulation, where the matrices are how we represent graphics or 3D graphics or video games. And it's also how we represent the data that we use to train neural networks. So you'll want to consider, if you get into deep learning, you'll want to consider how you get access to a large number of very powerful GPUs in order to do your deep learning, in order to train your neural networks. And we'll talk a little bit more about how people are gaining access to GPUs a little bit later in the talk. Now, one of the questions I get quite often is whether deep learning is just a fad. Is deep learning, this kind of, we have this AI spring or this AI summer, and AI will disappear just as it's had over the past several decades. And I don't think so. Part of the reason I don't think so is that we are going beyond GPUs to dedicated hardware that processes, that does these matrix manipulations. So going beyond just GPUs to these custom hardware components, as we see here in the latest iPhone X. So iPhone 10 now has a bionic chip. It's a neural engine that is specifically designed to do machine learning and deep learning. Now, the reason that you want something like this embedded on your device is not only that it's fast, but that it addresses security issues in that the data doesn't leave the device. But so the short answer is deep learning is here to stay, and it's going to start permeating all the devices that you see around you more than you've already experienced. So how does deep learning work in practice? The way to think about it is to step back and think about how exactly the human mind actually understands and recognizes patterns in the world around it. So you and I look at this screen, and we can see that there are numbers on the screen. We recognize that an 8, a 6, a 5 is different than a 4 and a 2. But how exactly are we able to do that? Well, it's not just that we understand patterns and differences between numbers, but we understand patterns and differences between numbers themselves. So while these are all different variations of 8s and 4s, we still understand that an 8 is an 8 and a 4 is a 4. And part of the way that we do that is that we notice subcomponents within sub-patterns within the patterns. So, an 8 has, for instance, a loop on the top and a loop on the bottom. A 4 has kind of a vertical line on the bottom and maybe a U shape at the top. So we're able to understand that there are distinct subcomponents within an individual item that we're recognizing. But how exactly do you program a computer to recognize this? Well, the first thing you would do is encode that number, that item that you're trying to identify as a numeric relationship between the elements of the object. So in this case, if we, there's a data set that many deep learning and even machine learning data scientists are familiar with called MNIST. And MNIST is a collection of handwritten numbers that where somebody collected, tens of thousands of numbers, captured them as images, and then made these available as training sets for data scientists to learn how to do deep learning. So in this case, you get a 28 by 28 pixel, a 28 by 28 image. So you have 784 pixels, and the variation of the pixels determine the pixel intensities or the numeric values of each of those pixels. But still, we get back to the problem that we were describing earlier, and that's how do you train a computer? How do you tell a computer that this is an 8 versus a 4? Well, the first thing we're able to notice, if you look at it in this respect, you notice that most of the image is actually zeros, and other parts of the images have some higher value up to 255, which would indicate a value of pure white, or a 0 meaning a value of pure black. So now we've encoded our data, and we need to feed that into some system that's going to understand and recognize the differences between these values. And this is where the concept of a neural network comes in. So if you think about an artificial neuron, you can think about a neuron as simply a placeholder for a number. So it's going to signify a number, and in this case, we're going to talk about a layer of neurons, and we'll talk about how those layers connect. But the first input layer of our neural network can just hold the values of the image. So we'll just say for every pixel that we have in our image, we'll have a neuron. So because it's 28 by 28 pixels, that's 784 pixels. So we'll create an initial input layer of neurons with 784 neurons, and we'll assign the value, that number that each of these neurons holds, as the value of that pixel intensity. A number from 0 to 200 from 0 to 254. Now, where the layer effect comes in, where the network effect comes in, is that we then take all of these neurons, the 784 neurons, and we connect them to other neurons within the network. And we connect them with what's called a weight. So the W would signify some weight that says the connection between the Y neuron and the input neurons is the value that neuron holds, weighted in some way, and then added in some way that we now capture some relationship between the neurons that are connecting into the second neuron. And we do that not just for one neuron, but we connect multiple neurons. So to kind of play back where we're going, we start out with an image, 28 by 28 pixels, 784. Each of those pixels has some pixel intensity from 0 to 254. And we're going to take each of those pixel intensities, each of those pixels, we're going to assign those to one of the 784 input neurons. And then we're going to connect each of those neurons to another layer of neurons where the inputs are weighted in some way. So what happens now is that the second layer of neurons, the bigger circles in this case on the right, start to aggregate information across the image. So now the subsequent layer of neurons is going to be able to start identifying patterns across the neurons that it's connected to. And we just keep doing this from the first layer of input neurons to what we call hidden layers. So the deep part of deep learning comes from the fact that we can now train more than just 2 to 3 layers of neurons. So prior to deep learning, we had what were called shallow networks. And shallow networks were only about 2 to 3 layers deep and weren't that complicated. They didn't have high accuracy, and they were challenged for, the neural networks were initially invented, over 50 years ago conceptually, but we had no way to train them. We didn't have the compute processing power like GPUs to do the computations. So we were stuck with shallow networks up until a little over a decade ago, where GPUs came on the scene, as well as the ability to do what's called backpropagation. And all of a sudden, we were able to create what were called deep networks. So networks where the number of hidden layers were, more than just 2 or 3. And nowadays, you would have up to 100 hidden layers within a neural network. And each of these layers connects both to the previous layers as well as the ensuing layers up to the output layer. And at the output layer, in this case, because we're trying to identify numbers that are from 0 to 9, the output layer only has 10 neurons. So going back to the beginning, we start out with an input layer on the very left that maps to the individual pixel intensities of the image, 784 input neurons, and we connect to multiple hidden layer neurons, and all those capture a pattern of, they're able to recognize a pattern within the image, and we'll talk a little bit about how that happens. And data flows from the input neuron to the output layer, and at the output layer, if we've trained our network properly, all of the output neurons will have a value very low, very close to 0, but the output neuron that represents the number 8 would have a value of 1. Ideally, if it was perfectly trained, saying that the neural network with very high confidence predicts that the input image represents the number 8. And if you, of course, input an image with the number 4, ideally, if it was a well-trained neural network, then the neuron that represents number 4 would be highlighted. That's the one that would resonate or have an output value closer to 1. And this is just a similar portrayal of that same kind of concept. Now we are kind of obviously going, we're obscuring the fact, what's happening in the middle, but we'll talk about this a little bit more over the next couple of slides. But I want to eliminate some confusion, because what we talked about before was that you would take an image, and every pixel in the image would be input into the input layer of the neural network, and that the neural network had 784 input neurons. But that's only because that's the job that we were tackling. We were trying to look at a 28 by 28 pixel image and map that to 10 output neurons. So that is only a type of neural network that would solve that specific problem. If you had an image that was 256 by 256 neurons, then the number of input neurons would be much higher. If you were outputting, trying to classify, say, breeds of dogs, and there were 4 breeds of dogs that you were trying to classify, instead of having 10 output neurons, you would just have 4 output neurons, one for each of the class of dogs that you were trying to classify. But it isn't just images that can be used with neural networks. What we can see here is that you can take text and also represent text in such a way that you can feed text into a neural network. And in this case, you might take a book, a paragraph, a play that was written, maybe a screenplay, maybe words from a movie, sort through all of the words, understand how those words were used within the movie, and train a neural network using words. And obviously, we wouldn't be able to represent the words as we've shown here. You would translate the words into a numeric value, and then create some type of useful prediction coming out of that neural network. So if you think about the way this might work in the case of a dog, so again, we would take the image, we'd break that image of the dog into pixels, and the first layer would take the values of those pixels. And what we kind of obscured in the previous slide is that depending on the type of neural network that you use, so there are recurrent neural networks, there are convolutional neural networks, there are neural networks with long short-term memory cells, neural networks that have attention mechanisms. There are different types of neurons within networks, and there are different ways that you connect neurons within networks. But the neural network that we're talking about earlier, where we're looking at images, are typically what are called convolutional neural networks. So a convolutional neural network is a type of network where you want to understand spatial relations between the input data. So if you have an image, you want to capture the values in the image in such a way that if you have 2 pixels in that image that are closely correlated, then you want the network to capture that correlation between images that are close together, or between pixels that are close together, as more important than pixels that are further apart. And you do this using what's called a convolution. And we won't be able to go into exactly how a convolution works, but what a convolution does is it starts with an input layer where every pixel is represented by an individual neuron, and in subsequent layers, we start to capture higher level relationships, higher level patterns throughout the image. So for instance, here in the second layer, you might start to identify edges. You might start to identify that certain pixels were darker vertically, or they were darker diagonally or darker horizontally. In the third, you might start to notice that edges kind of connect together and form arcs or form corners of a table, or in the case of an animal, you might start to notice circles where an eye was located or a nose was located, or edges where a tail was located. And by the time you get to the fourth and the fifth layer, you start to see higher level features of an animal, until in the output, you'd be able to output that this was a dog versus a cat. And sorry if we're kind of obscuring the details here, because I want to get beyond the neural network and talk about how these are trained. But where the complexity comes in with deep learning is that, as I indicated on the previous slides, I showed a neural network. I showed an artificial neuron as just this circle that holds a number. But in reality, those circles are more complicated. And I showed kind of one-line connections of one neuron to another neuron, and that isn't always true. Sometimes neurons connect to a subsequent neuron and then may loop back to a previous neuron. And this is an example of what's called the Neural Network Zoo, which was created by the Asimov Institute and shows different types of neurons. So the different colors here represent different types of neurons, whether it's a recurrent neural cell, a memory cell, a spiking cell, a probabilistic cell, so different types of cells. And then the ways that the cells are connected determine the type of neural network that you're working with. But in general, the ideas that we attempt to mimic in many cases with neural networks mirror what is happening within the brain itself. So in this case, you might think of that neural network that we talked about where the input are the pixels of an image is very similar to the input that hits your retina. So your retina has rods and cones. The rods and cones identify the different colors. They also identify the intensity of the light, and then they connect to different layers and different types of neurons within the brain, and kind of flow through until even in our own brain we're able to identify a cat from a dog. And so we are obscuring some of the issues here and going through the topic fairly quickly, but these slides are available, and I tried to make some of the image sources available if people want to go back later and look at some of these sources and dig a little bit deeper. So you might wonder, okay, great. So we have these neurons. They capture some value. They're interconnected in some way. How do I, as a data scientist, capture that programmatically? How do I program a neural network? And this is an example of what's called a convolutional neural network that would have been programmed in a language called Keras. So Keras is it's a Python-based language, and you very simply define each of the layers in your network. You'd have what's called a sequential network. So this, for example, is a feed-forward network where you have in the beginning 2 convolutional layers, followed by a pooling layer, a dropout layer, a dense layer, and additional layers, and you define certain aspects of those neural networks. And I think what's fascinating here is that very quickly, in a single screen, in less than 10 lines of code, you're able to define a neural network. The reality, though, is that it takes a while as a data scientist to understand what the input values here are. And, whether you'd have 2 convolutional layers or 3 convolutional layers, whether your dropout layer would have a 25% dropout versus a 50% dropout. But I just wanted to show you that it's both simple to program a deep learning network in a language like Keras, although it's still fairly complicated to understand how exactly you need to configure that network. So if you haven't done anything with deep learning to date, I definitely recommend looking at Keras and taking a course or two. It does take probably about 80 hours of online education to be able to be somewhat proficient with deep learning networks, but it also doesn't require 2 or 3 years of a PhD program to train a neural network. And now in the previous slide, what I talked about was how you would train, how you would build a neural network using Keras. The reality is that there are roughly a dozen popular network deep learning frameworks available right now, and these are a few of those deep learning frameworks. Now, here at IBM, what we've recognized is that while TensorFlow gets a lot of press in the news, every one of these frameworks has a specific target audience, a specific problem that they're very adept at addressing. So we don't think that any of these frameworks are going to win the AI battle, win the deep learning battle anytime soon. So we're taking a multi-framework approach to our deep learning strategy and planning to support a majority of these frameworks going forward. And the reality is that once you know how to train a neural network in any of these frameworks, you can take advantage of the other frameworks quite easily. You do have to learn a slightly different language, a different syntax, but even within a specific company, within data science teams within a specific company, we recommend that people don't get too stuck and hung up on adopting a specific framework, because different frameworks are adopted by different communities, and you want to go to the framework and work with the community that is trying to solve the problem that you are. And in most cases, companies can use deep learning to solve a wide range of problems. So, and we'll talk about this in a second, but find a community that's solving the problem that is most like the problem that you're trying to solve, and work with the framework that they're using, or at least understand that framework, and you can translate that framework into, look at the neural network and then maybe translate that neural network into a framework that you're more familiar with. But don't get hung up on, at this point, too early on a specific framework. Now, the reason for that is that, a question I get quite often is, should everybody just give up on the other frameworks and move over to TensorFlow? Has TensorFlow solved the deep learning problem? Is it the best and only way to develop your neural networks? And the simple answer is no. So TensorFlow has been out a couple of years. It is an amazing framework. You can do quite a bit with it, but we're already starting to see some of the weaknesses within TensorFlow. The most common is that it's a static computation graph, and solutions like PyTorch allow you to have dynamic computation graphs, and that allow you to have neural networks that kind of change over time. But in general, where we are right now in deep learning is, I'd like to say that we're more iPod days, very, very, very early in deep learning. We're nowhere near iPhone 10 in this kind of timeline. There's going to be some rapid evolution and rapid changes, but also I think a proliferation of frameworks. I would expect that over the next 5 years, we'll see less of a consolidation around TensorFlow, and quite likely see an expansion of other frameworks and other approaches to how people are doing deep learning. And in that context, let's talk about how deep learning is done in practice. So in practice, you have a team of people that are working with the data scientists to develop a deep learning solution. So in larger enterprise scale companies, you have people that have specialized with different skill sets, such as the data engineer that's maintaining the databases, the data sets, the data pools, lakes, and helping the data scientists extract the data, maybe even do some of the data prep. And even once the data scientist has prepared the data, built the model, trained it, they still need to meet a business need. And they're oftentimes working in close collaboration with the business analyst that is evaluating how well that model meets the needs of the business. And so there's oftentimes a back and forth between the business analyst and the data scientist to ensure that the data scientist really understands what the business goals are, and that the final model has the right accuracy and the right predictive intent to solve the business needs. And I'd be a little remiss to leave out the trainer. So in the bottom left, a significant challenge is not just getting the data from your systems, because oftentimes your systems have data, but the data hasn't been structured in a way that you can automatically train a neural network. So you might have heard about unsupervised and supervised training of machine learning models. And the supervised portion of training machine learning models occurs when somebody like a trainer labels the data for you. So this is an incredibly valuable skill where somebody is going out and either working with their internal community, maybe working with a company like Crowdflower, but labeling the data and making sure that high quality data is provided to the data scientist. And even once the business analyst and everybody else have approved the model, it still goes to the DevOps team who's going to deploy that model, the application developer who's going to use that model within an application. And what is oftentimes forgotten is that still isn't the end. You still want to monitor that model because, for instance, if you've built a fraud detection model, your model would be very good at detecting fraud in the beginning, but it's a cat and mouse game, and the fraudsters are going to try to trick your model. So your model's predictive capabilities would deteriorate over time. Or if you've created a product recommendation model, your audience's purchase behaviors will change over time, and you need to be able to adapt to those changes over time. Now, I just want to do a quick plug here for online courses like Coursera, Udacity, FastAI. A challenge that we have right now in data science and especially in deep learning is that there are very few people that know how to do deep learning and machine learning in practice. But there are a large number of people that are transitioning into this field, and this is these online resources are a great place where they can go to learn how to do data science. So let's just talk really quickly about how data science is done in practice. We've been talking about how you need to train a deep learning model, and I keep saying model as though there's just a single model that gets trained, but in reality, data scientists don't train a single model, they train hundreds or thousands of models. They explore a variety of neural network designs, data preparations, and hyperparameter spaces to find that optimal model. And they will go through these continuous cycles of create a network, tune the hyperparameters, test the model quality, realize that it's not quite what they need, and go back and do this iteratively. And the challenge in deep learning is, how do you do this? How do you iterate through and explore not just a single neural network, but hundreds or thousands of networks to find the one that's optimal for you? And the way that you do that is that you normally have a daily workflow when it comes to deep learning, where you're going to come up with your initial neural network design, you're going to plan experiments, you're going to then train those models overnight. So you'll oftentimes come up with a specific neural network that you're interested in, and you will train that model using the data that's available, maybe train 10 to 50 versions of that model, and then come back in the morning, look at the results, realize that there's a certain part of that model or a certain tweak to the data that you need to make. You'll redesign the neural network, you'll plan additional experiments, and you'll train another round of models. And you'll do this iteratively. Oftentimes over the period of 2 months, you may train 15 to 30 models overnight. Do that for a couple of months, and in the end, you'll have trained, several hundred to 1,000 different models, ultimately to find that one model that you want. And the question is, how do you do that efficiently? And so let's just walk through, at the end of this talk, of how you would do this in practice. So if you're lucky, you can start out with a data set. So there are a lot of data sets available online, and one of those is ImageNet 22K, where it's 14 million images, 3 terabytes. They've been categorized into here, 21,841 categories, but we just round that up to 22K. You've got your image data set, and now you've got to take those images and you want to classify those images into one of the 22,000 categories. Now, if you're lucky, somebody has already solved the problem that you are interested in. And if you go online, there's something called model zoos, neural network model zoos, which are lists of different networks that people have designed. In this case, for Cafe, which is a popular network, you can go to their model zoo, and they have a list of all the different networks that you can just download and work with. They have nice descriptions. So, say that you've got your model. So in this case, you chose a ResNet101 model, which is, we talked about those hidden layers, the deepness of a neural network. So this ResNet101 is 101 layers deep. So we've got our neural network, we've got our model, and what you would have to do is take that neural network and define it some way, define it in a framework. So in this case, we might choose Cafe to define our convolutional neural network. And, as I was saying, training a network takes a long time. So in this case, let's say that we have a pretty beefy server, one with 4 NVIDIA P100 GPUs, which is one of the latest generation of GPUs. We're going to take our data, we're going to train that model on these GPUs. And the shocking thing is that that amount of data trained on these very powerful GPUs will still take you 16 days to train. And now, if you remember, I said that data scientists don't just train a single model, they train hundreds to thousands of models. Well, if you're training hundreds of thousands of models, you have a significant amount of data. This could be 16,000 days of training time. So what you really want to do is you want to use something called data parallelism, for example. And instead of just training one model, you're going to train you're going to train a copy of your model. You're going to not just do it on one server, but you're going to do it on another server, and you're going to split your data across the servers, and you'll sync the training data. And now this is great because now instead of just training on one server, you're able to split the data, split the model, and train twice as fast. Now, what we've done here at IBM, and the way we envision how to do deep learning, is you want to spread out the model that you want to train not just on one server, but on multiple servers. So in this case, let's say we take our ResNet101 model, we spread it across 64 different servers. We put them on some very beefy, powerful, for instance, in this case, power system servers with 4 P100s, 4 P100 NVIDIA GPUs, and we find a way to sync the data or sync the training of that model across every one of those servers that are training the model simultaneously. And now with that same amount of data, we can get our training times down to 7 hours. And this is the problem that we're addressing here at IBM. We're looking at, how do we help data scientists train thousands of models as fast as possible with as much data as they can have available, but not, train over days, but to get that down to hours and to not be stuck at training one model at a time, but to be able to train train dozens or hundreds of models at a time. And the way that we're doing this is we're taking a similar approach of batch training models. We're using something called Kubernetes, which is a container orchestration service, and allowing users access to a server cluster that allows them to train models very quickly in parallel. And hopefully we'll have a talk about this upcoming service very soon. But for now, let me pass this back to Bill, and we'll take about 10 minutes to do some Q&A.
Hey, Anthony, thanks so much for that excellent presentation. So let's get started with today's Q&A session, and I want to thank the audience for their participation. Had a lot of questions that have come in, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Anthony if you'd like to contact him following today's webinar. So let's get started. Anthony, I guess there are a bunch of questions about applying deep learning. And we probably ought to start with a question, well, how do I tell if my company is ready to do deep learning or needs deep learning?
So you can tell if your company is ready for deep learning simply by the fact of whether your company is already doing machine learning, or even slightly before that, have some type of either a data science team or a business intelligence team, a team of people that is dedicated to understanding the data that flows through your company. And sometimes what I call the process of going from either a business intelligence group or a business analyst group to doing deep learning is what I call cognitive business process transformation. So first, you've got to build up data science skills within your team, build up the quality of the data that you're capturing. Not always the quality, don't focus on the quantity as much as the quality of that data, like very clean data and highly correlated and connected data, but then build up the skills within the team. And as I showed earlier, you don't necessarily have to go out and hire a team of all PhD researchers. It is important to have a couple of people, at least one person on the team that's skilled in machine and deep learning, but they can typically guide and start to grow a team of machine and deep learning data scientists over time. Typically, it takes I think for companies that are just starting out, it can take a couple of years to develop proficiency.
Well, thank you, Anthony, for that answer. Some more specific questions about applications of deep learning. The first one I think is very interesting, and that is, does deep learning have a role in classical retail and marketing analytics like retention, acquisition, and segmentation, where we've been using classical statistical machine learning all this time?
So that's an interesting question, and it gets down to the type of neural networks that are available and the type of question that you're asking. So there are convolutional neural networks, and convolutional neural networks are ones that are used for looking at spatially correlated data. So image data or data that like audio data, or data where there's some correlation between the data points, how close they are either in space or in time. There are recurrent neural networks, and those are for time series data, so data that changes over time. For instance, music or like language translation. But there are other types of networks you can use that could be used for classification. So being able to classify that an individual is more or less likely to churn. So what I would recommend, and to be honest, some of that research into customer retention and churn is more, I'd say, at the research stage within deep learning. But that doesn't mean to not look into it. It actually means now is probably the time, if something like that is really critical to your company, to start looking at the research that's happening, because you can gain a competitive advantage. So what I would recommend is just doing a search for, whatever topic you're interested in, and just add the word deep learning. And you may get referred to research articles, but again, don't shy away from that, because if you wait until a lot of these answers for something like customer retention are all, the deep learning solutions are all productized and off the shelf, at that point your competitors might have already moved, and you'll have they'll have first mover advantage.
Right. Excellent point. One of our audience members asked what I think is a pretty obvious question, and that is, how do I explain hidden layers and deep learning to a business executive to make them want to get involved in this?
So this talk was definitely a little more technical. We plan to have another talk that is more focused on the executive and the business unit discussion. This talk was meant to be a very fast review of neural networks, but also a little bit more focused on it from a data science perspective about how deep learning is done in practice. But it would be nice to have a talk on how do you explain deep learning to executives, and the short answer is don't talk to them about hidden layers or input and output layers, unless you want to put them to sleep. Yep.
I thought that was an excellent point. It's a tool. It's going to work. A couple of technical questions that I think are interesting. In classical machine learning, statistically based machine learning, the output of a model is an algorithm that we can implement. What is the output of a deep learning neural net? Is it an algorithm that we can implement in the same way in our operational systems?
So the beauty of neural networks is that the output of a neural network is fairly static, in that you have neurons, you have the weights between those neurons, and you have a statically defined network, a network that you can actually burn into a chip, because it doesn't change. Its ability to predict is of course dynamic depending on the data that's input to it. There are algorithms that get applied during the training process, but you can really think of a neural network as, when you're done, you don't really have an algorithm as much as you have a static matrix of relationships between the neurons that have a predictive ability. All of the algorithms are used during the training phase and are become hard-coded by the time the training is completed.
Oh, an interesting difference. We keep hearing about explainable AI or explainable deep learning. Can you comment briefly on what that is and whether or not we can even hope for that?
I think that we will in the future have what we're calling XAI, or lowercase x AI, for explainable AI. But I think we're going to have to accept that at some level, I don't think that neural networks will ever be 100% explainable, because they're based off of neurons, biological neurons, and we can't even explain most of the time how we come to the conclusions that we come to. But there is this concept that people are working on of playing back a network. So having a network kind of show layer by layer how it's representing data. So the best example are convolutional neural networks, where I was talking early on that on the input layer, you are literally giving it the individual pixel values, and the output layer is giving you the classification. But as the data goes through, you start seeing higher level representations of the spatially correlated patterns within the data. You can look at every one of those layers, and you literally start to see that at the beginning you're just seeing lines and edges, but by the time you're looking at the last layers, they really start to look like noses and eyes. And but if you so you can go online and do some searches, and you'll find images for convolutional neural networks where people are kind of playing back what an individual layer, how an individual layer is representing the knowledge that it's, the patterns that it's recognized within images that it's been trained with. So the answer is,
thank you.
Yes, there's some explainability, but not complete. It's really a research project right now.
Hey, fun presentation. Thank you. Great answers to some very good questions. For those of you that asked questions today that weren't answered, we'll be sending all the unanswered questions to Anthony and the IBM Watson team so they can follow up with you after today's webinar. I have just a few quick announcements. If you'd please mark your calendars for November 30, that's just 2 days from today. That's our next Data Science Central webinar, which is going to be Advanced Tools for Dynamic Visual Analytics, which will be sponsored by SAS. Also remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close, and I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to IBM Watson for their sponsorship, and particularly to our speaker, Anthony Stevens, for his insight into today's topic. This is Bill Vorhies. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on November 30th. Have a great day.